Assalamu alaikum. Welcome to the lecture 11 of Unit First. One more protection that we need for SERs include gate protection. We have three techniques for this. The first technique is the simplest gate protection technique. It involves one resistance and one diode. This resistance is used to provide the protection against a high current, and this Zener diode is used to provide the protection against the high voltage, or we can say to provide the protection against over voltage. Our current exceeds if our gate current exceeds beyond its value, beyond its specified value, it leads to damage to the SER. Similarly, if our voltage increases beyond its value, it may lead to false triggering of SER. Thus, protection against both these over voltage and over current is done by for the over current we are using this resistance, and for the over voltage we are using the Zener diode. This less technique that we are using for the gate protection. Next gate protection technique is where we are using one inductor, one resistor, and the Zener diode. This Zener diode, its function is same like the previous technique, that is, it provides protection against the over voltage. While as this inductor, it provides the protection against the rapid current variations, and hence protects the thyristor from the damage. This resistance increases the dV by dt capability of SER. The another technique is where we are using combination of diodes, resistance and resistances, and the capacitor. It provides the protection from every kind of unwanted triggering. Here the diodes are used to protect the gate terminal from the negative voltage, and this is done by the rectification process. Here the resistors are used to limit the current. Resistance R1 is used to limit the current, and the R2 provides the dV by dt protection. Here one capacitor is used to remove the high frequency components. This is the overall um, gate protection scheme that we are using. Triggering circuit for thyristor. Triggering or firing means turning on of SCR. Normally, thyristors are switched on by supplying a voltage signal at the gate terminal of the device. This is done with the help of this gate drive circuit that we called as driving circuit or triggering circuit or firing circuit. The main aim of this triggering circuit or this firing circuit is to produce the gate cathode voltage across the gate cathode terminals. The thyristor turns on as soon as this Vg exceeds the critical gate trigger voltage at the particular turning on angle or triggering angle alpha. For ideal switching, we should have adequate amplitude of current of short duration and short rise time for turning on of SCR. Or we can say the thyristors can be turned on by a slow rising rectified signal, just like this, by a sharp single pulse, by a constant magnitude DC signal, or by a train of high frequency pulses. The main function is whenever this Vg voltage exceeds this VGT, that represents the V gate triggering voltage or critical voltage, uh, this thyristor is turned on at that particular angle, that is this triggering angle alpha. This thyristor is turned on from that instant. This gate cathode voltage depends upon gate to cathode junction temperature, anode current, and the supply voltage. A typical waveform for the gate current is shown in this figure. Here, In this waveform, we have higher initial value of gate current with a very fast rise time. The initial high value of gate current is then reduced to a lower value where it stays for several microseconds in order to avoid unwanted turning off of the device. The initial high magnitude and rapid rise in gate current quickly turns on the device as as the spread carriers spread mm, throughout the layer of the blocking junction J2. This decreases the switching losses and increases the initial di by dt capability of the device. Normally, gate signal is not required continuously. Only, or we can say, except inductive loads where a continuous triggering pulse is required. For a high power applications, we need to isolate the control and triggering circuit from the power circuit. Otherwise, the high voltage and the high current transients may lead to maloperation or damage to the low power control and triggering circuit. For this, we need pulse transformers or optocouplers. And for the high power applications, we need fiber optical cables that are used to isolate the control circuit from the power circuit. Or we can say a thyristor conducts only when it is properly biased or when the trigger source of a trigger circuit supplies that required minimum gate voltage, which is represented by VGT, that is the gate triggering voltage, and the required gate current, that is represented by IGT. General layout of firing circuit. This is the general layout of the firing circuit, which consists of this is the control circuit, this is the driver circuit, which itself consists of the pulse amplifier and the pulse transformer, and this is the power circuit. This control circuit consists of a pulse generator, which is fed from the AC as well as the DC, and to produce the AC pulses or DC pulses as required. These voltage pulses are then supplied to this pulse amplifier, that is the part of this driver circuit for the amplification purpose. These shielded cables transmit the amplified pulses to the pulse transformers. The function of this pulse transformer is to isolate the low voltage gate cathode circuit from the high voltage anode cathode circuit. And from this pulse transformer, these pulses are given to the SCRs. This firing circuit should fulfill the two main functions. One function is that, and as we know, this power circuit consists of number of SCRs. This means that the firing circuit should produce gating pulses for each SCR at the proper desired instant. Which means that, for example, in case of a single phase semi-converter which consists of two SCRs, the triggering circuit must produce one firing pulse in each half cycle. That means in each 180-degree cycle, it must produce one triggering pulse to one SCR, and in the next cycle, it must produce one pulse to the another SCR. Similarly, in case of a three-phase pulse converter having 6 SCRs, gating circuit must produce one trigger pulse after every 60-degree interval. The second function is that this control signal, as and the pulses are produced here by this control circuit. Why we are using this driver circuit? The main function as of this driver circuit is one is this amplification and another is this isolation. That means if we are feeding these pulses directly to the SCR, these may not be able to turn on these SCRs. It's therefore necessary to feed these pulses, voltage pulses, to a driver circuit and then to the power circuit. And then, if we say what is the function of this driver circuit, we can say the primary function of the driver circuit is the pulse amplification, and the second primary function of this driver circuit is the electrical isolation. The secondary functions of this circuit include the short circuit protection. It provides us, and the second point is it provides us the blanking time or the dead band um, during the turning on and off of SCRs. The various firing circuit schemes include the most commonly used three types of schemes, that is DC gate triggering, AC gate triggering, and another one is UJT triggering. Now, firstly, we are explaining this. What is this DC gate triggering? That means we are here, we are turning on the SCR by applying a DC gate to cathode voltage. When we are applying a sufficient gate cathode voltage, this may cause turning on of SCR, or we can say when our gate triggering voltage is greater than our critical gate voltage, that is whenever our VG is greater than VGT, it starts conducting at that particular angle alpha, which is called as triggering angle. But it suffers from a disadvantage, that is, since in case of a DC, we are providing the continuous DC signal, which may cause the gate power loss. This is the DC gate triggering circuit. Here we have applied the step voltage, step DC voltage. This is the load, and this is the thyristor, and this is our firing circuit, which simply consists of a simple potential divider. Here R1, R is the variable resistance and R1 is the fixed resistance. This R1 provides the path for the gate current. Both the R and R1, they are in kilo ohms. Here, if resistance R is high, the voltage drop across this resistance will be high, which may cause less voltage across the resistance R1. As the voltage across this resistance, as the as VG, which is the gate triggering voltage, is the voltage that is build up across this resistance R1, we should keep it in mind that this voltage VG, that is the voltage across this R1, it should not be less than VG minimum, or the current across that should not be less than IG minimum. If the VG is less than VG minimum, or IG is less than IG minimum, or SCR will not get turned on. So our main aim is to if is to lesser to decrease the voltage across this resistance R by decreasing the value of resistance, such that the voltage across this resistance R1 should be such that the VG should be equal to VGT, gate triggering pulse, where it should cause turning on of the SCR. The main advantage of this triggering method is that if we do not want to trigger the SCR, this can be easily done by increasing this value, the value of this resistance R. By increasing the value of this resistance R, the voltage buildup across this will be high, and across this potential divider, the voltage across this R1 will be lower, and this may cause and since the resistance R1 voltage across this is lower, and if this is lower than the IG VG minimum, or IG is less than IG minimum, or SCR will not get turned on. Or we can say the main advantage is that it is the simplest firing scheme, and this as disadvantages already discussed, that here we are having, since we are applying the continuous gate current, we are having the continuous power losses. Now the AC gate triggering. This AC gate triggering includes resistance triggering and resistance capacitance triggering. This resistance capacitance triggering is further divided into half wave RC triggering and the full wave RC triggering. Let us continue with the first one, that is the R triggering. Now the AC resistance triggering. Here we are applying the AC voltage. This is the simplified circuit of this resistance. This is the circuit of this resistance triggering. Here this is the AC voltage. That means we are applying. This is the source voltage represented by the sinusoidal AC voltage that has the positive cycle and the negative cycle. And this is the peak, as we know that peak of an sinusoidal wave is at 90 at omega t is equal to 90. This is the load, and the voltage across this is represented by plus minus E subscript L. And this is the thyristor, and this represents the triggering circuit, AC triggering circuit, which consists of this R minimum resistor. This is the variable resistor. This is the diode. The main function of this diode is to prevent the flow of current during the negative cycle. That means the current the triggering current flows only through the positive cycles. And this is the resistance RB. We have to build up the voltage across this terminal, across this resistance RB. If the voltage across this RB, that means if the VG is equal to our gate triggering voltage, then we can say our SCR gets turned on. This resistance triggering circuit, this suffers from the disadvantage that in this case we have a limited firing angle control, that is from 0 to 90 only. um, if the main motive of this triggering circuit is to build up the voltage across this resistance RB, and this can be done if we lower the resistance of this R V. That means if the resistance value of the resistance is high, the current across the path will be low. Similarly, the voltage across this resistance will also be lower. To generate the voltage across, to produce the voltage across this RB, the main we need to decrease the voltage of this. We need to decrease the resistance of this RB. Lesser the resistance of this RV, higher the value of current across the path, higher the value of the current, the voltage across this RV will be higher. And if the voltage across this RV is equal to VGT, our SCR will get turned on at that triggering angle alpha. And this is the source voltage, the sinusoidal voltage. This represents that at an angle of alpha, if the voltage across the SCR, that means from 0 to alpha, as firstly this is the source voltage, this is the voltage across the load, and this is the anode to cathode voltage, that means the voltage across the SCR. Firstly, from 0 to alpha, since no triggering is done, that means SCR is not turned on. If SCR is not turned on, that means this behaves like the open circuit, and SCR is not turned on. The voltage drop across this load will be zero. Since this is the open circuit, current across this load will be zero. If the current will be zero, the voltage across the load will be zero. That means from zero to alpha, the voltage across this load will be zero. Since since this behaves like the open circuit, the voltage across the SCR will be same as our source voltage. That's why I am showing from 0 to alpha. This is our source. This anode to cathode voltage or voltage across thyristors, exactly it follows our source voltage. Once the SCR is triggered at an angle of alpha, If the SER is triggered at an angle of alpha, this means the current will flow. SER is turned on. If the SER is turned on, the current will flow through this path through this load, and the voltage across the load will be exactly the voltage across the, that means this VL will be equal to our source voltage. That's why I am showing here from alpha to pi, this is following our source voltage. If here we have the at angle of 90, omega t is equal to 90, we have the peak. Similarly, I am showing in case of load, this will be the pi, this will be the peak. And if it is decreasing at an angle of 180, similarly I am showing in case of load, it's decreasing at an angle of 180. Since no triggering pulse is provided during the negative cycle, that's why there will be no load across the there will be no load across the there will be no voltage across the load. Similarly, at an angle of 180 plus alpha, again, because the positive cycle starts, that means again the pulse is given to the SCR at an angle of 180 plus alpha. Again, the SCR will trigger at an angle of 180 plus alpha to 2 pi. If we are considering this voltage across thyristor, as already I have told you that during 0 to alpha, this behaves like the open circuit. That means the voltage across thyristor, since it behaves like the open circuit, this V anode to cathode voltage will be exactly equal to source voltage. That's why I am showing from 0 to alpha, it's following the source voltage. Once SCR is triggered on, that means this behaves like a closed path. If this is the closed path, that means the voltage across thyristor will be hardly 0 to 1 volt. That's why I am showing it nearly 0. This is once the SCR, that means during that interval when the SCR is turned on, that means from alpha to pi, and here from 180 plus alpha to 2 pi, I am showing the voltage across the SCR will be 0. But during the reverse voltage, that means during this negative cycle, since I am saying no triggering pulse is provided, since no triggering pulse is provided, that means this again behaves like the open circuit. If this behaves like the open circuit, the V anode to cathode voltage will be exactly equal to source voltage. That's why during this negative cycle, I am representing here, I am showing here that this V anode to cathode voltage, that is the voltage across the SCR from pi to 2 pi, it's exactly equal to my source voltage, that is the negative cycle. Here, in any case, alpha can never be greater than 90. This is the maximum limit for the alpha. Since we can increase the voltage here by only decreasing this resistance RV, once we increase this voltage, across this RB, this results in the lower alpha values. That means the highest range for this alpha is 90, and the lower range will be less than 90. 90. That means the triggering angle range in this resistance R, in this R triggering, is from 0 to 90.